Queries with aggregates, Part 1. In addition to simple expressions that we introduced in the last lesson, SQL also supports the use of aggregate expressions, or functions, that allow you to summarize information about a group of rows of data. With the Pixar database that you've been using, aggregate functions can be used to answer questions like, how many movies has Pixar produced? Or, what is the highest grossing Pixar film each year? Select ag function, column or expression as aggregate description. Without a specified grouping, each aggregate function is going to run on the whole set of result rows and return a single value. And like normal expressions, giving your aggregate functions an alias ensures that the results will be easier to read and process. Common aggregate functions. Here are some common aggregate functions that we are going to use in our examples. Count star or count column. A common function used to count the number of rows in the group if no column name is specified. Otherwise, count the number of rows in the group with non-null values in the specified column. Min column. Find the smallest numerical value in the specified column for all rows in the group. Max column finds the largest numerical value in the specified column for all rows in the group. Average column finds the average numerical value in the specified column for all the rows in the group. Sum column finds the sum of all numerical values in the specified column for the rows in the group. Grouped aggregate functions. In addition to aggregating across all rows, you can instead apply the aggregate functions to individual groups of data within that group, i.e., box office sales for comedies versus action movies. This would then create as many results as there are unique groups defined by the group by clause. Select ag function, column or expression as aggregate description from my table where constraint expression group by column. The group by clause works by grouping rows that have the same value in the column specified. Exercise. For this exercise, we are going to work with our employees table. Notice how the rows in this table have shared data, which give us the opportunity to use aggregate functions to summarize some high-level metrics about the teams. Go ahead and give it a shot. Find the longest time an employee has been at the studio. For each role, find the average number of years employed by employees in that role. Find the total number of employee years worked in each building. SQL Lesson 11. Queries with aggregates, Part 2. Our queries are getting fairly complex, but we have nearly introduced all the important parts of a select query. One thing you might have noticed is that if the group by clause is executed after the where clause, which filters the rows which are to be grouped, then how exactly do we filter grouped rows? Luckily, SQL allows us to do this by adding an additional having clause, which is used specifically with the group by clause to allow us to filter grouped rows from the results set. The having clause constraints are written the same way as the where clause constraints and are applied to the grouped rows. With our examples, this might not seem like a particularly useful construct, but if you imagine data with millions of rows with different properties, being able to apply additional constraints is often necessary to quickly make sense of the data. Did you know that if you aren't using the group by clause, a simple where clause will suffice? Exercise. For this exercise, you're going to dive deeper into the employee data at the film studio. Think about the different clauses you want to apply for each task. Find the number of artists in the studio without using a having clause. Find the number of employees for each role in the studio. Find the total number of years employed by all engineers. SQL Lesson 12, Order of Execution of a Query. Now that we have an idea of all the parts of a query, we can now talk about how they all fit together in the context of a complete query. Each query begins with finding the data that we need in a database, and then filtering that data down into something that can be processed and understood as quickly as possible. Because each part of the query is executed sequentially, it's important to understand the order of execution so that you know what results are accessible where. Query order of execution. Number 1, from and joins. The from clause and subsequent joins are first executed to determine the total working set of data that is being queried. This includes subqueries in this clause and can cause temporary tables to be created under the hood containing all the columns and rows of the tables being joined. Number 2, where. Once we have the total working set of data, the first pass where constraints are applied to the individual rows, and the rows that do not satisfy the constraint are discarded. Each of the constraints can only access columns directly from the tables requested in the from clause. Aliases in the select part of the query are not accessible in most databases, since they may include expressions dependent on parts of the query that have not yet executed. Number 3, group by. The remaining rows after the where constraints are applied are then grouped based on common values in the column specified in the group by clause. As a result of the grouping, there will only be as many rows as there are unique values in that column. Implicitly, this means you should only need to use this when you have aggregate functions in your query. Number 4, having. If the query has a group by clause, then the constraints in the having clause are then applied to the grouped rows. Discard the grouped rows that don't satisfy the constraint. Like the where clause, aliases are also not accessible from this step in most databases. Select. Any expressions in the select part of the query are finally computed. Number 6, distinct. Of the remaining rows, rows with duplicate values in the column marked as distinct will be discarded. Number 7, order by. If an order is specified by the order by clause, the rows are then sorted by the specific data in either ascending or descending order. Since all the expressions in the select part of the query have been computed, you can reference aliases in this clause. Limit/offset. Finally, the rows that fall outside the range specified by the limit and offset are discarded, leaving the final set of rows to be returned from the query. Conclusion. Not every query needs to have all of the parts we listed above, but a part of why SQL is so flexible is that it allows developers and data analysts to quickly manipulate data without having to write additional code, all just by using the above clauses. Exercise. Here ends our lessons on SQL queries. Congrats on making it this far. This exercise will try and test your understanding of queries, so don't be discouraged if you find them challenging. Just try your best. Find the number of movies each director has directed. Find the total domestic and international sales that can be attributed to each director. SQL Lesson 13, Inserting Rows. We've spent quite a few lessons on how to query the data in a database, so it's time to start learning a bit about SQL schemas and how to add new data. What is a schema? We previously described a table in a database as a two-dimensional set of rows and columns, with the columns being the properties and rows being the instances of the entity in the table. In SQL, the database schema is what describes the structure of each table and the data types that each column of the table can contain. Example, correlated subquery. For example, in our movies table, the values in the year column must be an integer, and the values in the title column must be a string. This fixed structure is what allows a database to be efficient and consistent despite storing millions or even billions of rows. Inserting new data. When inserting data into a database, we need to use an insert statement, which declares which table to write into, the columns of data that we are filling, and one or more rows of data to insert. In general, each row of data you insert should contain values for every corresponding column in the table. You can insert multiple rows at a time just by listing them sequentially. Insert into my table, values, list of values. In some cases, you have incomplete data and the table contains columns that support default values. You can insert rows with only the columns of data that you have by specifying them explicitly. In these cases, the number of values need to match the number of columns specified. Despite this being a more verbose statement to write, inserting values in this way has the benefit of being forward compatible. For example, if you add a new column to the table with a default value, no hard-coded insert statements have to change as a result to accommodate that change. In addition, you can use mathematical and string expressions with the values that you are inserting. This can be useful to ensure that all data inserted is formatted in a certain way. Exercise. In this exercise, we're going to play Studio Executive and add a few movies to the movies to our portfolio. In this table, the ID is an auto-incrementing integer, so you can try inserting a row with only the other columns defined. Since the following lessons will modify the database, you will have to manually run each query once they are ready to go. Toy Story 4 has been released to critical acclaim. It had a rating of 8.7 and made 340 million domestically and 270 million internationally. Add the record to the box office table. Oh. Interesting. SQL Lesson 14, Updating the Rows. In addition to adding new data, a common task is to update existing data, which can be done using an update statement. Similar to the insert statement, you have to specify exactly which table, columns, and rows to update. In addition, the data you are updating has to match the data type of the columns in the table schema. Update my table, set column equal to value or expression, other column equal another value or expression, where condition. The statement works by taking multiple column value pairs and applying those changes to each and every row that satisfies the constraint in the where clause. Taking care. Most people working with SQL will make mistakes updating data at one point or another, whether it's updating the wrong set of rows in a production database, or accidentally leaving out the where clause, which causes the update to apply to all rows. You need to be extra careful when constructing update statements. One helpful tip is to always write the constraint first and test it in a select query to make sure you are updating the right rows, and only then writing the column value pairs to update. Exercise. It looks like some of the information in our movies database might be incorrect, so go ahead and fix them through the exercises below. Pardon? Both the title and director for Toy Story 8 is incorrect. The title should be Toy Story 3 and directed by Lee Unkrich. SQL Lesson 15, Deleting Rows. When you need to delete data from a table in the database, you can use a delete statement, which describes the table to act on and the rows of the table to delete through the where clause. Delete from my table where condition. If you decide to leave out the where constraint, then all rows are removed, which is a quick and easy way to clear out a table completely, if intentional. Taking extra care, like the update statement from the last lesson, it's recommended that you run the constraint in a select query first to ensure that you are removing the right rows. Without a proper backup or test database, it is downright easy to irrevocably remove data, so always read your delete statements twice and execute once. Exercise. The database needs to be cleaned up a little bit, so try and delete a few rows in the tasks below. Mm-hmm. Andrew Stanton has also left the studio, so please remove all movies directed by him. SQL Lesson 16, Creating Tables. When you have new entities and relationships to store in your database, you can create a new database table using the create table statement. Create table if not exists, my table, column, data type, table constraint, default value. The structure of the new table is defined by its table schema, which defines a series of columns. Each column has a name, the type of data allowed in that column, and an optional table constraint on values being inserted, and an optional default value. If there already exists a table with the same name, the SQL implementation will usually throw an error. So to suppress the error and skip creating a table if one exists, you can use the if not exists clause. Table data types. Different databases support different data types, but the common types supporting numeric, string, and other miscellaneous things like dates, booleans, or even binary data. Here are some examples that you might use in real code. Integer or boolean, float, double, real, character with the number of characters, or variable character, or text. The text-based data types can store strings and texts in all sorts of locales. The distinction between the various types generally amount to the underlying efficiency of the database when working with these columns. Both the character and varchar, variable character, types are specified with the max number of characters that they can store. Longer values may be truncated, so can be more efficient to store and query with big tables. Date and date time. SQL can also store date and time stamps to keep track of time series and event data. They can be tricky to work with, especially when manipulating data across time zones. Blob. Finally, SQL can store binary data in blobs right in the database. These values are often opaque to the database, so you usually have to store them with the right metadata to requery them. Table constraints. We aren't going to dive too deep into table constraints in this lesson, but each column can have additional table constraints on it, which limit which values can be inserted into that column. This is not a comprehensive list, but will show a few common constraints that you might find useful. Primary key. This means that the values in this column are unique, and each value can be used to identify a single row in this table. Auto increment. For integer values, this means that the value is automatically filled in and incremented with each row insertion, not supported in all databases. Unique. This means that the values in this column have to be unique, so you can't insert another row with the same value in this column as another row in this table. Differs from primary key in that it doesn't have to be a key for a row. Doesn't have to be a key for a row in the table. Not null. This means that the inserted value cannot be null. Check expression. This allows you to run a more complex expression to test whether the values inserted are valid. For example, you can check that values are positive or greater than a specific size, or start with a certain prefix, etc. Foreign key. This is a consistency check which ensures that each value in this column corresponds to another value in a column in another table. For example, if there are two tables, one listing employees by ID and another listing their payroll information, the foreign key can ensure that every row in the payroll table corresponds to a valid employee in the master employee list. An example. Here's an example schema for the movies table that we've been using in the lessons up till now. Create table, movies, ID, integer, primary key, title, text, director, text, year, integer, length, length, minutes, integer. In this exercise, you need to create create a new table for us to insert new rows into. Create a new table named name version download count SQL Lesson 17, Altering Tables. As your data changes over time, SQL provides a way for you to update your corresponding tables and database schemas by using the alter table statement to add, remove, or modify columns and table constraints. Adding columns. The syntax for adding a new column is similar to the syntax when creating new rows in the create table statement. You need to specify the data type of the column along with any potential table constraints and default values to be applied to both existing and new rows. In some databases, like MySQL, you can even specify where to insert the new column using the first or after clauses, though this is not a standard feature. Removing columns. Dropping columns is as easy as specifying the column to drop. However, many databases, including Postgres and SQLite, don't support this feature. Instead, you have to create a new table and migrate the data over. Renaming the table. If you need to rename the table itself, you can also do that using the rename to clause of the statement. Other changes. Each database implementation supports different methods of altering their tables, so it's always best to consult your database docs before proceeding. Our exercises use an implementation that only supports adding new columns, so give that a try below. Add another column named language. SQL Lesson 18, Dropping Tables. In some rare cases, you may want to remove an entire table, including all of its data and metadata. And to do so, you can use the drop table statement, which differs from the delete statement in that it also removes the table schema from the database entirely. Drop table if exists my table. Like the create table statement, the database may throw an error if the specified table does not exist. And to suppress that error, you can use the if exists clause. In addition, if you have another table that is dependent on columns in the table that you are removing, for example, with a foreign key dependency, then you will have to either update all dependent tables first to remove the dependent rows, or to remove those tables entirely. We've reached the end of our exercises, so let's clean up by removing all the tables that we've worked with. We've sadly reached the end of our lessons. Let's clean up by removing the movies table. There's more topics. Subqueries. You might have noticed that even with a complete query, there are many questions that we can't answer about our data without additional post or pre-processing. In these cases, you can either make multiple queries and process the data yourself, like an animal, or you can build a more complex query using SQL subqueries. Example: let's say your company has a list of all sales associates with data on the revenue that each associate brings in and their individual salary. Times are tight, and you now want to find out which of your associates are costing the company more than the average revenue brought per associate. First, you would need to calculate the average revenue all the associates are generating via select average revenue generated from sales associates, and then using that result, you can then compare the cost of each of the associates against the value. To use it as a subquery, you can just write it straight into the where clause of the statement or of the query. Select star from sales associates where salary is greater than select average revenue generated from sales associates. As the constraint is executed, each associate's salary will be tested against the value queried from the inner subquery. A subquery can be referenced anywhere a normal table can be referenced. Inside a from clause, you can join subqueries with other tables. Inside a where or having constraint, you can test expressions against the results of a subquery, and even in expressions in the select clause, which allows you to return data directly from the subquery. They are generally executed in the same logical order as the part of the query that they appear in, as described in the last lesson. Because subqueries can be nested, each subquery must be fully enclosed in parentheses in order to establish proper hierarchy. Subqueries can otherwise reference any tables in the database and make use of the constructs of a normal query, though some implementations don't allow subqueries to use limit or offset. Correlated subqueries. A more powerful type of subquery is the correlated subquery, in which the inner query references and is dependent on a column or alias from the outer query. Unlike the subqueries above, each of these inner queries need to be run for each of the rows in the outer query, since the inner query is dependent on the current outer query row. Example: instead of the list of just sales associates above, imagine if you have a general list of employees, their departments, engineering, sales, etc., revenue, and salary. This time, you are now looking across the company to find the employees who perform worse than average in their department. For each employee, you would need to calculate their cost relative to the average revenue generated by all people in their department. To take the average for the department, The subquery will need to know the department each employee is in. Select star from employees where salary is greater than. Select average revenue generated from employees as department employees where department employees dot department equals employees dot department. These kinds of complex queries These kinds of complex queries can be powerful, but also difficult to read and understand, so you should take care using them. If possible, try to give meaningful aliases to the temporary values and tables. In addition, correlated subqueries can be difficult to optimize, so performance characteristics may vary across different databases. Existence tests. When we introduced where constraints in Lesson 2, the in operator was used to test whether the column value in the current row existed in a fixed list of values. In complex queries, this can be extended using subqueries to test whether a column exists in a dynamic set of values. Select star from my table where column in or not in subquery. When doing this, notice that the inner subquery must select for a column value or expression to produce a list that the outer column value can be tested against. This type of constraint is powerful when the constraints are based on current data. SQL topic: unions, intersections, and exceptions. When working with multiple tables, the union and union all operators allow you to append the results of one query to another, assuming that they have the same column count, order, and data type. If you use the union without the all, duplicate rows between the tables will be removed from the result. Example: select column, another column from my table, union or union all, intersect, except, select other column, yet another column from another table, order by, column, descending, limit, n. In the order of operations as defined in Lesson 12, the union happens before the order by and limit. It's not common to use unions, but if you have data in different tables that can't be joined and processed, it can be an alternative to making multiple queries on the database. Similar to the union, the intersect operator will ensure that only rows that are identical in both result sets are returned, and the except operator will ensure that only rows in the first result set that aren't in the second are returned. This means that the except operator is query order sensitive, like the left join and right join. Both intersect and except also discard duplicate rows after their respective operations, though some databases also support intersect all and except all to allow duplicates to be retained and returned. All right, that's all for SQL Bolt. RIP.